Okay, let us begin. This is the final part of the lecture number 2. So, I hope you still remember what was happening before. And let me begin with the following. So, what we are discussing is basically the notion of analyticity for complex functions. So let me put my glove, because I don't want to, let's say, use my greasy hands on the screen. Now it's better. You see, everything is falling. I have a glove, and we can now continue. So let me change the color, and this is the underlining. So just remember, it is quite important to understand that the terminology that we introduced before regarding the so-called analytic function was done illegally. It was not really justified to use the same term of analyticity that we are talking about. But as we are going to prove soon, we will show that every function which is C differentiable, it has a derivative C differentiable, this function is in fact also analytic. So we will recall again from the, let's say, from the calculus, the notion of analyticity, and we will adapt it to the concept of the complex functions. So let me start considering the situation. So okay, suppose U contained in C is a domain and f that goes from U to C is a complex function. So what does it mean? So this is my U. Okay, remove something here and take this is out. You know what is the greatest thing about teaching mathematics? Because it is so artistic. You can actually make pictures. You can make pictures, all kinds of the pictures, and maybe those pictures do not really show anything artistic, but they are so exciting. That's great. You make a picture, look at this, wow, what it could be. And I say, this is the domain U. And here we have the function. So this function is here. Come on. There is the function f, and it goes to C, to another plane. So that's the situation. So let me come back and continue the definition. So the definition is the following. The function f is said to be, and there now is the term analytic in the domain U if and only if and only if for every, so let's write it down, for every Z0 belonging to U, there exists a power series And let me write down this power series. This is the power series. n is equal 0 to infinity, and this is an z minus z0 to the power n. So this power series is centered at z0. There exists a power series, and now we have to say something convergent in a disk. And let me put it like this: z such that z minus z0 is smaller than epsilon for some epsilon larger than 0, and since this is convergent, we also have that my function f of z is equal, and we write it down, and this is equal, n is equal 0 to infinity, and we are getting here an z minus z0 to the power n, and this is exactly the value. So there's two values. One is represented by the infinite series, another given by the function, but they are the same. So this representation, call it start. The formula star shows that the function f of z can be represented by the power series around the point z0. Okay, let me go back. Let me show you. So okay, this is my point z0, and then we claim there exists an epsilon larger than 0. So we have a little disk around it. So let me write it down. Yeah, that's a epsilon. This is the radius, epsilon larger than 0. And in this disk, this function f of z has the formula, power series expansion formula star. So that is called the power series representation. So this is power series representation, or it is also said this is Taylor series of f of z. This is also said Taylor series of f of z. So if we are talking about find the power series representation of the function f of z, then of course this is one of the things. So now let me indicate a couple of properties. So notice that by the observations from the previous class, that by our observations from the previous class, we can differentiate power series term by term, which gives us, let's say, so if I have here f of z0, if you notice, if I put in f z0 here, so this is z is equal to z0, this will be 0 here, you see this one, this value is 0 for n larger than 0, so if z is equal to to the 0, so this will be 0 for n larger than 0. I replace, so it gives me that in such a case, I'm getting here that this one is equal a0. On the other hand, since we can write it down here, let's put it here, the derivative of f of z, I can write it down, this is d dz of the power series n is equal 0 to infinity, an, and this is z minus z0 to the power n. So that one gives me the derivative from n is equal 1, because constant will definitely disappear. So this will be an times n, and then I'm getting here z minus z0, and this will be n minus 1. So we obtain that the first derivative of z0 at that point is exactly the coefficient, put it here, a1, and in such a case this would be times 1. This is my 1. And similarly, if you continue doing it, then you will notice that z0 n derivative will be just an times n factorial. And consequently, maybe I should write it in red, an times n factorial. And then immediately you can make the following statement. So statement. If f of z is analytic and given by formula star 10, in this formula an, the coefficient, is actually nothing else than the derivative, n derivative of the function f of z divided by n factorial. So remember, any analytic function is infinitely many times differentiable, and if you want to find the Taylor series or power series expansion, power series representation of this analytic function around a given point z0, you have to find all the derivatives of this function, and the coefficients will be given by that particular formula, by this particular formula. So for a moment we don't know if the C differentiable functions are analytic. We didn't prove it. This is going to be one of our next goals of our next lecture. I don't want to do it in this lecture. I prefer to present you with the series of examples of expansions of the analytic, let's say, analytic functions. So we'll show, and this is the first example, that some of the functions are analytic. So notice that we have here several examples that are easy to handle. That means we have a function and we can present this function as a power series. So let me start with our series of examples. So we start with the example number 1. And in this example, I'll just simply consider a number, a complex number. So, okay, good. Maybe not complex number, not complex number. Consider a domain. And I put here like this: D is equal to Z such that Z, not nice, why it starts writing not nicely? Z minus, no minus. Z is just simply smaller than 1, and the function f from D to C given by f of z is equal 1 divided by 1 minus z. 1 minus z. Of course, you look at this function, of course you say, okay, I know what is this function. This function is defined, the domain of this function. Notice that the domain of this function is exactly the set of all z such that z is different than 1. But here I'm considering it restricted to the smaller domain. So this is like in the previous picture. I have a function which is defined on the larger domain U. So my domain U is actually, in this case, this domain of the function. So this is my U. And now I'm looking at the point 0, and around the 0 I take a small disk of radius 1, which is exactly this disk. This is our disk of radius 1. And then you say, okay, if I look at this function only in this little disk, then you see that that's a familiar formula. I have actually immediately knowledge of its power series expansion, because it's nothing else than the geometric series z to the power n. That's the geometric series. So we already have seen this. This is the geometric series. Geometric series. And to be sure, you must understand this is converges if z is smaller than 1. Of course, when you have this, that means that's the power series representations of that function. So this is exactly the power series of this function. But is this function analytic? Question. Is the function f of z equals 1 minus z analytic? And put it like this, c minus 1, which is our u. Is this function analytic? And in that case, you have to check the condition of the analyticity. In this case, you have to look what does it mean. You have to take any arbitrary point z0, any arbitrary point z0 from this domain and show the power series, such a power series expansion exists. So you have the formula star, this formula star here. This is exactly the formula that we need to show can be applied to that function. So let's do it. Okay. So take an arbitrary z0 belonging to, okay, z0 belonging to u, and assume that z0 is not equal to 1. So, okay, no, that means, so that means, simple, okay. That means z0 is not equal to 1. And rewrite and write. One over 1 minus z. I can represent it. This will be like 1, and this will be 1 minus z0 minus z. Let me do it longer. And this will be minus z0. And then I have here, yes, you see, notice this and this come with the plus and minus. So basically they cancel each other. So clearly we have this equality. And this, of course, can be done. So what do I do here? Let me continue. I can now pull out, because z0 is not equal to 1, so I can, this one is different than 0, so I can pull it out. So I pull it out, and this is 1 minus z0 is taken out, and then I'm having here the following expression. This is 1 minus, and this will be z minus z0. This is divided by 1 minus z0, and put it also in the bracket. Put it also in the bracket, and I see, wow. So that looks very familiar, like here. You see, do you remember we were using this here? This is our power series expansion of this. This is geometric power series expansion. So it's 1 minus z something. So let me write it down again. So we have actually this formula that we're really excited about. That if you take n is equal 0 to infinity, q to the power n, that's my geometric progression, and that one is minus q. So this is this formula. So if I say that one is my q, this is my q. If this is my q, then means if z minus z0 divided by 1 minus z0, that's my q, so I take absolute value. Modulus is smaller than 1, then the series, then it is 10, maybe 10, we have the convergent, sorry, 10, that's, sure, 10 for q equals z minus z0, 1 minus z0, the geometric series, and this will be like this. N equals 0 to infinity. Qn converges. Okay, so that gives us a possibility to continue. So we are here, so we can write this, and now we go to the new line, and we will write it again, equals, and let me look again, because I want to copy it correctly. So it will be 1 minus z0, and here we have the geometric series, n is equal to 0 to infinity, and I can write it down. It is simply z minus z0 to the power n, 1 minus z0 to the power n, and now enter this one back into the formula, and I'm getting here, this is n is equal to 0 to infinity, and this will be 1 over 1 minus z0 to the power n plus 1, and this will be z minus z0 to the power n, and you immediately recognize that that's a number. Sorry, something is not nice. I have to make sure that there are no red, let's say, bad symbols. And so you can immediately recognize that this is your coefficient in this series. This is your an, and the series is convergent by that particular observation. And we get the equality. So we just proved, we showed. So we proved that the function f of z equals 1 minus z is analytic. Maybe we need to apply again. Okay, let's see what would be. So example, find, okay, is the function, and I say this function, the new function, maybe I change the symbol, g of z equals 1 divided by 1 minus z square analytic. That's a question. Maybe is this function analytic? So there is some kind of resemblance. You see, you have one function. We show this is analytic. But what is this function? What is this function? This function is probably, let's say, let's compute the derivative of f of z. So what do I get here? I'm getting here it is equal to 1 minus z squared. So the derivative minus 1 minus and derivative. Yeah, that's the derivative of that function. So in this way we know that if I have the power series expansion for that function here, for the function f of z, I can use this power series expansion and obtain the power series expansion for the derivative, which is the function g. So this is n is equal to 0 to infinity, and this will be n, and this will be 1 minus z0 to the power n plus 1, and this will be z minus z0, and this is n minus 1, because we just applied here the derivative with respect to dz, and that's what we got. So that's the first example, and now we can definitely look at other examples. So we already know that there is a kind of a relation between the derivatives, and if you take the derivatives and the differentiations of the power series in order to that means this relation can be used in order to obtain the power series expansions of certain elementary function, which of the different type, namely of the type which is described here. So let me go to the next example, and we start again. So maybe we do it example number 2. This is an important example. Consider, it is based basically on the previous observations. So consider a point. Let's call this point A belonging to C. So it can be any complex number, and f of z equals, and f of z equals, okay, I put it like this, z plus a, just to write it a little differently, z plus a. Very good. Show that a, the function f of z admits a power series expansions around any point z0 different than a, minus a actually, different than minus 8, minus a. That means simply f of z is analytic, and the b, find the radius of convergence of these expansions, of this power series expansion. Okay, let's do it. Solution. So we are definitely inspired by the previous example, and we know that our main goal here is to apply the geometric series idea in order to convert this function into a power series. So let me write it down. What we know, that 1 minus q for any complex number, and this will be n is equal 0 to infinity, this is qn, if the q is smaller than 1, converges, and we have let's say this inequality, this representation. So let me write it down. F of z is equal and here, what do I have here? And here I have let me write 1, and this is a plus z. It was z minus 8, but I changed the order, so I hope you don't mind. I changed it later. So I do the following. So I said, okay, z0 different than minus a. So I can write it down like this. This will be a, and this will be minus, so this will be plus z0, plus, and this will be z, and this will be minus z0. So as you see, this is again the same expression, that z0 here and z0 here cancel. So I'm actually I do not modify this particular. Okay, I do not modify it. So continue, and now I say I can take this out. This is not equal to 0. This is different than 0, so I can take it out, and I'm getting here, this is a plus z0, and then I have here 1, and here I have here 1 plus z minus z0 divided by a plus z0. Looks good. Looks good. And then I say, it's not exactly what is written here. You see, it's not exactly what is written here. Not exact. What should I do? I should make it exactly like that. Okay, so this is equal. So I put it a plus z0, and then I put here 1, and this is 1, and I put here minus, and this will be minus z minus z0. Maybe move up. I don't like to be in the corner. Divided by a plus z0, and that one, in this case, of course, what you see that your q is actually equal to minus z minus z0, a plus z0. So you know that this will be exactly the power series, geometric power series, convergent if q is smaller than 1, strictly smaller. Of course, it will be divergent if it is larger than 1. So that means I'm getting immediately that this condition is actually equivalent to say that z minus z0 must be smaller than a plus z0, and this is your radius of convergence. So you're actually in this moment will be able to include in your solution the answer to the question B. So let's continue. So I put here like this, continue, this thing is equal, and I copy that guy. This is a plus z0, and then I have here n is equal 0 to infinity, and I have here minus 1. So remember, here we have here minus 1, so I just simply write it down, minus 1 to the power n, because you take the power q to the power n, so this will be q to the power n, you see here, so that means minus 1, and this one separately, so then I can use that value, the rest as a z minus z0 to the power n divided by a plus z0, a plus z0, and I see, or I get my power series expansion, which actually concludes this question. I have here everything finished. This is just simply a plus z0 to the power n plus 1, and that's the coefficient, and n, and we know when it is convergent. Let me illustrate it on the picture. So here we have here coordinate system. We just remember the convergence is determined by that condition. So not nice. Nothing disappears. So here we have here A. Let's say this is my point A. Suppose this one is my point Z0. So this is minus A. Yeah, this is my minus A. So that point is minus A, and this one, this has the length Z0 plus A. So this is the distance between the value of minus A and Z0. Minus A and Z0. And then, of course, if this is the center and that's the radius, so your circle looks like that. Notice that your function is not defined at minus A. So this is actually out of the domain. So the domain of your function here is everything such that domain of your function f is everything such that z is different than minus a. So that's your domain. So what is the radius of convergence? So radius of convergence is the distance from the point that is not belonging to the domain of that function. We call these points singular points. So this is the distance, from z0 to the singular point. Minus a of f of z. So one more time, in this case we have here that the radius of that the disk that is around the z0 is the maximal disk that fits entirely, open maximal disk of the radius r that fits in the domain of the definition of the function f, the domain of the definition of the function f. So yeah, this is nice. And now maybe let's do another problem, kind of a similar. So let's say, yeah, I'm in the mood of problems, so let's do another example. So example, consider A and consider B belonging to C. A is not equal to B, make sure, and can underline, put here 2 dots, and the function f of z is equal 1, and I put here z minus a, and this will be z minus b. So remember, so what is the domain of this function? The domain of this function is everything in a complex plane except a and b. So that means a and b are singular points of f. So what are the singular points? A proper definition of a singular point is any point in the plane that function is not analytic. That means function has no power series expansions there. And that's exactly, if something is not in the domain, how we can consider the power series expansion there? Of course not. So this function. So we have this function. So let z0 belongs to C, and we assume that z0 is not equal to A and B, and we will show the function is analytic. We will find the power series expansion of f of z around z0. Okay, let's do it. So I'm doing it. So first thing I'm looking at is, it's interesting. So I do the following. Partial fraction decomposition. So I put it like this. This is equal z minus a. This is z minus b. I want to decompose it as the sum of two partial fractions. And this is plus b z minus b. So of course you put them together. Then you are getting a z minus b plus b z minus a. And this is z minus a, z minus b. You compare this number here with the two numbers here. You obtain two equations, namely a plus b is equal to 0, and maybe, yeah, minus ba plus, minus ab is equal to 1. Or you can just simply take the expression 1 is equal. So you need to solve either this system of equation or just simply take this expression z minus b plus b z minus a. So that means compare two expressions and say, okay, this is supposed to be true for every z. So I can take even the forbidden z. So call it like this, put here like this, z is equal to a. So what do I get? On the left is still 1. This one is gone, and I'm getting a, and I'm getting here a minus b. And then I put here z is equal to b, so I'm getting again this is 1, and on the right hand side I'm getting b, and this is b minus a. So immediately I'm getting this one is equal a is equal 1 divided by a minus b, and b is equal minus 1 divided by a minus b. Okay, so therefore I can continue down and I can rewrite the formula, namely I can write it down that f of z is equal, and here I'm having, this is 1, and this one is equal a minus b, and using this representation over there, I'm getting 2. This is 1 z minus a, and this is minus 1, and this is z minus b. And then I continue and I do the similar things. Think about this as two power series of the geometric series. So I remember my previous example, and I will be applying the same idea. So I put it like this, z minus z0 plus z0 minus a, and that one, not good. I have to, sorry, I won't fit it in the one line, and that's unfortunate. So I restart it here, and I put it again 1 over a minus b, and here I have here again 1, and this will be z minus z0 plus z0 minus a. So you notice these two cancel, so I'm getting exactly this expression here. So that is correct. And then I can write it down minus, and I do the same thing with the second one. Z minus z0 plus z0 minus b. And here I will add it, and now extend that one too, and now I pull out that coefficient. So I pull out this coefficient out. So let me write it now already in kind of a ready form. So I'm pulling it out, so this will be z0 minus a, and here I'm getting here 1, and this is 1. And since this will be plus, I'm moving it to the first position, so this will be plus. So I'm getting here 1. Sorry. What I'm doing? Oh, I'm getting, okay. This is 1 plus, okay, I will do it in the 2 steps. So this will be z minus z0 divided by z0 minus a, and this is minus, and the same here, z0 minus b, and I'm getting here 1, and that one is equal 1 plus z minus z0, and this one is z0 minus b. And of course, you look again at the geometric series. The geometric series 1 minus q is equal sigma q to the power n. Let me show you. This is the geometric series that you are looking at. So this geometric series means that here we can think about that one as this is minus q. For that one, this will be another minus q for that, because you have here the sign minus, so you should not forget it, that you have to take it into account, and then you just continue and you write it down 1a minus b, and here we have here 1 z0 minus a, and then we have infinite series n is equal 0 to infinity minus 1 to the power n, and that one is equal z minus z0 to the power n, and that one is equal z0 minus a to the power n, and this is minus, and similarly 1 over z0 minus b, and here we have n is equal 0 to infinity minus 1 to the power n, and this is z minus z0 to the power n, and this one is equal to z0 minus b to the power n, and close the bracket. So that's the formula. We have to simplify it. So in order to simplify it, let me continue. So we just simply say, okay, in order to simplify, you just put everything together and make it one sum, one infinite sum. So 1a minus b. So what do? Let me just accelerate in it. I put that one here, I put this one here, and then I convert this difference of the two power series into one power series. So that is going to be, and this is going to be n is equal to 0 to infinity. We have here common factor. I can take it out. This is also a common factor. So I'm getting here that minus 1 to the power n, and here I have here 1 divided by z0 plus minus a to the power n plus 1 minus 1 over z0 minus b to the power n plus 1. Close that one, and this is z minus z0 to the power n. To complete it, you can just enter this 1a minus b inside, and this gives you the required power series. So it's going to be, write it down like this, minus 1 to the power n, a minus b, and here we have here 1 z0 minus a to the power n plus 1 minus 1 z0 minus b to the power n plus 1, and here we have z minus z0 to the power n, and of course means that's a power series. This is your coefficients a n. So we proved that we have here power series expansion, at the point z0, and we found it explicitly. So one little remark, notice that Here actually we are dealing with two series. You have two series here. One series is here, so this is my first series, and this is the second series. So it is clear that first series is convergent for z minus z0 smaller than z0 minus a, and the second series is convergent for minus z0 smaller than z0 minus b. You see, for minus b, absolute value, this is absolute value. So you can look at the picture. What does it mean? That means you have here again the coordinate system. You have 2 points. Let's say this is my point A, this is my point B. They are both singular points, so they are not in the domain. And then you take the point Z0, and you're looking. The first series is convergent in this disk. The second series is convergent in that disk. Where the radius of convergence for the first series is this, so like R1, and the radius of convergence for the second one is R2. But you see, you want them both to be convergent, so of course they both will be convergent on the smaller one. So smaller disk is exactly the one that gives you the radius of convergence, so that means this is smaller disk. Then you can say that the radius of convergent is the distance from Z0 to the closest closest singular point of f of z. I'm writing so ugly. F of z. Hey, do I have some space? Yeah, let's use some space just to make sure that we add one more. So example. Find the power expansion of f of z equals 1 over 1 plus z squared around z0 equals to 0. Okay, solution. Let's do it. So f of z, you can say this is equal 1 minus z squared. And again, the idea of power, let's say power series, provides you with the answer. This will be n is equal to 0 to infinity minus 1 to the power n, and then you have here z to the power 2n, and that's your answer. This is your answer. We will do occasionally more power series expansions. We just need to prove our main theorem. This is so-called the Taylor expansion formula for C differentiable functions, which basically will tell you that C differentiability and analyticity in this particular sense are indeed the same. That means we were not really abusing the terminology. We were just simply using this terminology with the insight, knowing in advance that it's going to be true, that it's going to happen, that will show that actually these two concepts coincide for the complex analytic function. I should strongly emphasize that analyticity in the case of the real single value function may be much more complicated. There are C differentiable functions, infinitely differentiable functions, real functions, have all the derivatives, but they are not analytic. There are many of such functions. And in such a case, we have to understand that the complex differentiable function is very, very different for real differentiable function. In the case of the complex differentiable functions, they're all nice. They're all analytic. Why we call a function analytic? Because it is good for analysis. Analytic analysis. You want to know more about the function. You have the power series expansion. And this power series expansion provides you with the keys how to deal with this function. Analytic means you can express it as a power series and use this power series, for example, for approximations, for your computations. Your computer doesn't know what's a function. Your computer only knows what are the numbers. So by using the Taylor series approximations, you can always handle analytic complex functions by doing it simply by truncating the power series expansion and taking it as approximation, putting in your machine computer, do your computations, and get your coronavirus results so you can definitely predict when it is all going to kill us all. Thank you.